Okay, there we go. Now it is recording full screen. Okay. Math now. I think. Okay. So, as the title implies, today we're discussing random variables. So, first of all, what is a random variable exactly? That we spent the first couple weeks discussing this whole idea of sample spaces and probability measures and blah blah blah. And there's a wide variety of different types of sample spaces and events that we might want to consider. The idea behind random variables is that you can take a large class of sample spaces and reduce them to a much smaller class of random variables that have similar properties and reduce the number of different types of probability spaces and sample spaces that you may want to consider. Oh, that's where this idea of random variables coming in. That instead of messing with the raw sample space, you may want to assign a number to each possible outcome in your sample space and then record that instead. So, simple example of a random variable, let's say you flip a coin 3 times. Well, in this case, our sample space is the number of different possible ordered outcomes. You could have 3 heads, you can have 2 heads and a tail, heads, tails, heads, heads, tails, tails, etc., etc. The set of possible events would just be the power set of that, a fairly large thing. But to make our lives simpler, you could define a random variable y to be the number of heads. Then for each item in the outcome space, then the y is a function where the input to the function is an item in the outcome space and the range is just a real number. So for example, y of heads, heads, heads gives you 3, y of heads, heads, tails gives you 2, y of heads, tails, tails gives you 1, etc., etc. So formally, a random variable y is a real valued and measurable function defined on a probability space. That is a function with domain of the outcome space and range the real numbers, and every point in omega maps to a real number that we denote as y of omega. And you can also define an inverse image under y of a given subset of real numbers to be the set of omegas such that y of omega is an element of whatever that subset is. So for example, on the previous slide, if B were just a singleton set containing 3, the inverse image of 3 would be heads, 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 because that's the only way you can get 3 heads. If B were the singleton set containing 2, the inverse image would be heads, heads, tails, heads, tails, heads, tails, heads, heads, all the possible outcomes where there's exactly 2 heads. And the definition of a random variable requires that the inverse image of any Borel set in the real numbers is an element of the set of possible events. And this is necessary so that you can assign probabilities to random variables without getting into the weird contradictions that I described a couple weeks earlier. If you're a master's student who never intends to take 760, then you can probably forget this as soon as you finish this homework. If you're planning on taking 760, then you'll need to remember this because you'll have to go through and prove that you don't get contradictions if you define random variables this way. Oh, a random variable, as I said, is a set function that takes values on the real line, or it could be could in principle take values on Rn. For the time being, we're going to restrict it to the case where there's only a single real number, and usually we don't mention the fact that it depends on an input variable from the sample space of omega. You usually just write y to denote a random variable rather than y of omega. The convention is random variables are usually denoted by capital letters, and the different values that a random variable can take on are denoted by lowercase letters. So the random variable corresponding to the number of heads in the previous example I gave you would be denoted by big Y. If I wanted to say what's the probability that big Y equals 3, you would use little y to correspond to 3 in that type of case. An even simpler coin toss example, if you just tossed a coin a single time such that your outcome space is either heads or tails, then y of heads is obviously equal to 1, y of tails is obviously equal to 0, and this illustrates the fact that you can define probabilities on your random variable in addition to probabilities on your outcome variable, that we can say the probability of heads is 1/2, but we can also say that the probability of the random variable equals y, or the random variable y is equal to 1, is also equal to 1/2. So some additional examples of random variables is that if you roll the die, the possible outcomes are obviously 1, 2, 3, 4, 5, 6. You can define your random variable y to be just the outcome of the die roll, and in that case you can say that the probability that y of omega is equal to any specific value omega, or maybe I should have said little y there, is just equal to 1/6. And you can also do stranger and more convoluted examples if you really want to. Say, for example, that your omega is the set of all integers 0, plus or minus 1, plus or minus 2, etc. So we could just arbitrarily define a random variable that the random variable is equal to A if the input variable from the original sample space is less than or equal to 0. Y of omega is equal to B if it's greater than 0. So to compute the probabilities in that case, the probability that y is equal to A would be the sum of 0 plus all the negative values of the outcome space, and the probability that y is equal to b would just be the sum of all the possible positive outcomes in the sample space. I mean, I don't know why you would ever define this random variable in practice, but just illustrates how this whole thing works. So far, so good on random variables. Okay. Oh, now we will discuss distribution functions, which are associated with every random variable. Distribution functions are used to describe the behavior of a random variable. The cumulative distribution function of a random variable y is a real valued function defined to be the probability that the random variable, it's usually denoted by a capital F, and capital F of y is defined to be the probability that the random variable is less than or equal to whatever given value you feed into the function. So, very simple examples. Say you roll the die again. If we assume it's a fair die, all heads are equally likely. We could get 1, 2, 3, 4, 5, 6. the probability of getting less than or equal to y when you roll a die is just going to be y over 6. Hopefully that's fairly obvious. It's the probability of getting less than or equal to 1 is 1 over 6. The probability of getting less than or equal to 4 is 4 over 6, etc., etc. And survival function of y is defined to be 1 minus the CDF. You see this mainly when you do survival analysis, which probably most all of you will have to take at either the master's or the PhD level at some point in the future. It's not something we'll use heavily in this class, though. Couple properties of the cumulative distribution function f of y. For starters, it's always between 0 and 1 because it's a probability, and probabilities are always between 0 and 1. The limit as y goes to minus infinity has to be 0 because that becomes the probability of y less than or equal to minus infinity, which is an outcome space that's become increasingly smaller, so that goes to 0. Similarly, the limit as y goes to infinity is equal to 1. It's always a non-decreasing function that if a is less than b, then f of a is less than or equal to f of b. This follows from the fact that the probability y less than or equal to a is always a subset of the event that y is less than or equal to b, so by the properties of probability that implies that f of a is less than or equal to f of b. F is right continuous, which may not be quite as obvious, but basically that has to do with the fact that it's defined on the previous slide to be less than or equal if you take the probability y less than or equal to a plus epsilon. As epsilon goes to 0, that's going to converge the probability is less than or equal to a, so hence it's right continuous. However, it does not necessarily need to be left continuous. You can create distribution functions where there are occasional jumps. And you can also show fairly easily that the probability that y is between a and b is just going to be f of b minus f of a. All of these are fairly straightforward to prove rigorously using the probability properties that I've discussed earlier. So, the reason random variables are nice is because all probability questions about a random variable can be answered via its cumulative distribution function. And more formally, given any sort of arbitrary sample space, set of events, and probability measure, you can create a random variable y with a sample space on the real numbers, set of events being the Borel sets, and a cumulative distribution function defining the probability measure. Okay, mostly said all this, blah, 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 blah. Basically, you can take any sort of abstract sample space and convert it to a random variable. So, why are we doing all this? This is just crazy math to torture first-year graduate students. Well, not entirely. The reason that one might want to do this is it allows you to come up with a unified framework for dealing with a large different class of possible events. Like, say, for example, let's consider, for example, one event is you flip a coin, count the number of heads, and that's going to be a random variable that's either 0 or 1. Well, you could also define an event where you roll a die and count the number of times you get a roll between 1 and 3. That's a random variable that's also a random variable that's equal to 1 with probability 1/2 and 0 with probability 1/2. Or you could do something, you draw a card from a deck of cards and count the number of times you get either a club or a diamond. Well, once again, that's a random variable with probability 1 equal to 1/2 and probability 0 equal to 1/2. In other words, a wide variety of different events can all be modeled using the same set of random variables. Well, if you can just find the properties of this particular random variable that I just described, then you can use it to describe the properties of a large number of real-world events. And I think most of this I just said, but you can ignore this abstract notion of sample space and focus your attention to the random variables and the properties of these random variables that we've defined. And if you can talk about the sample space of random variables, which will be the values in R that a random variable can take on. And the CDF, or the properties of the random variable in general, don't contain information about the original sample space. As I just described, this random variable that's equal to 1 with probability 1/2, 0 with the probability of 1/2, could correspond to a wide variety, in fact an infinite variety, of different real-world events. Or another example, say you toss a coin n times, the number of heads and the number of tails will have the same distribution, and the random variables defined as the number of heads and the number of tails will have the same distribution, even though they're not the same. They're not the same events that we're looking at here. And a definition is that two random variables x and y are identically distributed if for every possible Borel set in the real numbers, the probability that x is in that particular Borel set is equal to the probability that y is in that particular Borel set. So this coin tossing example that I just gave, x and y are identically distributed because the probability of, assuming the coin's fair, the probability of getting 3 heads is exactly equal to the probability of getting 3 tails, even though they're obviously not the same random variable here. And it's this theorem that's in Cassell and Berger. You can show that the following two statements are equivalent, that the random variables x and y are identically distributed, and their distributions, their cumulative distribution functions have the same value for every possible value of x. The proof of this gets so hairy that Cassell and Berger just basically say it's too hard and they're not going to do it. If you're a master's student, you can just take my word for it that it's true. You may get to see the proof of it someday if you take 760. An important point here is that you can have two random variables that have the same distribution even if they're not equal to one another. The number of heads and the number of tails from the same coin toss have the same distribution, but they quite clearly are not equal to one another. Or for example, the number of heads from the roll of from a coin toss, or the number of values between 1 and 3 from the roll of a single die are completely independent of one another. One doesn't tell you anything about the other, but they also have the same distribution. And this is an important distinction to keep in mind later on when we talk about convergence, that when we say like two random variables converge to the same distribution, that doesn't mean that they're eventually going to become the same random variable. It just means that the distributions will be the same.
So when you say they're equal, you're saying they're describing the same underlying events. Like if two random variables are equal, they're both describing the exact same thing. They're both describing the number of heads.
I mean, they're not necessarily describing exactly the same thing, but if one, if the first random variable is equal to 1, then the second one is equal to 1 as well, sort of thing. It's trying to think of an example of that that isn't completely contrived. If ridiculous example, it's the first one that pops into mind. Say I have a magic die such that whenever my coin lands heads, this die always lands a 2, something like that. And if it's tails, it always lands a 5. Then, even though they're not describing the same event, the two random variables I just described would be identical to one another. Yeah, well, if you know the value of one random variable, you would know the value of the other with absolute accuracy. And in that case, they would be identically distributed as well, but you can also have cases where they're identically distributed but not equal to one another. If the die and the coin are independent, then those two random variables have the same distribution, but they're not equal to one another. This will become important later on, as I said, that we'll discuss types of convergence, that you can have things that converge in distribution, meaning that they'll go to the same distribution, but there's no guarantee that they'll ever be equal to one another, or you can have them converging to one another in probability, meaning that the probability that they'll be different will become smaller and smaller, etc., etc. We'll cover all this in more detail later. The important thing to remember for now is just because things have the same distribution doesn't mean they're the same. Okay. So, random variables y are traditionally classified into discrete and continuous random variables. This classification is a little bit arbitrary. If you take 760 and get into more advanced measure theory, you'll learn that discrete random variables are actually equivalent to continuous random variables given a certain measure, that the way continuous random variables and their distribution functions are defined in terms of integrals actually is equivalent to the summations you use for discrete random variables given an appropriate measure. If you're not taking 760, then just ignore everything I just said, and I apologize if I caused any pain in your brain when I said it. But for the purposes of this class, we're just going to pretend they're different with different properties. You'll learn in 760 how they're actually equivalent. But in any event, with that introduction, discrete means that the random variable takes on only a finite number of values, or at most a countably infinite number of values, or continuous means that the range of y covers at least some subsets of the real line or some intervals. And you can also have mixed random variables, which would be that here the probability that, basically what this distribution function is saying is the probability that it's equal to 1 is equal to 2/3, or I take that back. It would actually be 11/12 minus 2/3. There's some discrete value. I should not try to do math in front of a room in my head when I haven't really slept, but there's some discrete probability that this random variable is equal to 3 or 2 or 1, but between 0 and 1, it's continuous, that there's a certain probability that's between that range, but the probability that's going to be equal to any given number is 0. And this will make more sense once I describe discrete and continuous random variables in more detail. In practice, I don't think anybody ever really uses these mixed random variables for anything, so if this made no sense, you can just ignore it, because I very highly doubt we will encounter it again unless I feel like being sadistic on the homework. So, discrete random variables. As I said before, if a random variable y takes on only a finite or countable number of values, then you can compute the cumulative distribution function just by summing over all the possible values that it can take on. That the probability that big y is less than or equal to little y is just the probability of, is just the sum of the probability that y is equal to z for all the z's that are less than or equal to y. This can either be finite or countable, but by definition of a discrete random variable, it's at most countable, so this summation makes sense. And as I said, if the sample space of y is just y1, y2, etc., then you can say that the cumulative distribution function is the sum of the probabilities that y is equal to every possible value below whatever little y is. And the probability mass function or frequency function associated with a discrete random variable is defined to be the probability that the random variable is equal to some given little y. Note that the probability mass function is usually denoted with a lowercase f, whereas the cumulative distribution function is usually denoted by an uppercase f. So another way we can write the cumulative distribution function is that we can just say capital F of y, the cumulative distribution function, is just the sum of the probability mass function over all the z's that are less than or equal to y. And similarly, we can calculate the probability mass function in terms, we can calculate the probability mass function in terms of the cumulative distribution function, where if y1 up to yn are the ordered possible values of the random variable y, then the probability mass function for yi is just the cumulative distribution function at yi minus the cumulative distribution function at yi minus 1. That's, in other words, it's the probability that y is less than or equal to yi minus the probability that y is less than or equal to yi minus 1. Since those values are ordered, that tells you that that's exactly equal to probability that big Y is equal to yi. So, simple example, say y is a random variable that takes on the values 0, 1, or 2 with probability 0.5, 0.3, and 0.2 respectively. Won't even ask about this one because hopefully it's just an insult to your intelligence if I did. But the little f of 0, the probability that this random variable is equal to 0 would be 0.5. The probability that it's equal to 1 is 0.3. And the probability that it's equal to 2 is 0.2. Hopefully that's straightforward enough. So, some properties of the probability mass function. We talk about the domain. This isn't only true for discrete random variables, by the way, and we talk about the domain of a random variable. That's the set of all values of the random variable for which the probability mass function is greater than 0. So if you tossed a coin 4 times and counted the number of heads, the domain would be 0, 1, 2, 3, 4. That's the different number of heads that you can observe. You cannot observe 5 heads. You cannot observe minus 1 head. You cannot observe the square root of pi over 17 heads. The at little f of y for all those other numbers would be equal to 0. And by the definition of a discrete random variable, the probability mass function will be greater than 0 for at most a countable number of values y. For anything that's not in this countable set, the probability mass function is going to be equal to 0. And if you sum the probability mass function over all possible values in the domain of the random variable, they all have to sum up to 1. Hopefully that makes intuitive sense. The probability of the full sample space has to be equal to 1. So the probability of all possible events in the sample space also has to sum up to 1. And obviously this implies that the probability mass function is going to be less than or equal to 1 over the entire domain. Well, over all possible y's, because if y is not in the domain, then it's equal to 0. But the probability mass function will be no greater than 1 for all y. So what's the probability mass function of a constant random variable? That is a random variable which is equal to some value k with probability 1 and equal to 0, just equal to k with probability 1. Well, the probability mass function would just be f of x equals 1 when x is equal to k, and f of x equals 0 anytime x is not equal to k. Hopefully that all seems reasonable enough. So, a couple examples now. Say we define the following probability mass function that y can take on the values 1, 2, 3, 4 up to infinity, countably infinite in this case, and the probability mass function, the probability that big Y equals little y is just going to be equal to 1 over y times y plus 1. Is this a valid probability mass function? Well, I mean, it satisfies most of the properties. It's 0 for all but a countably infinite number of values. It's never greater than 1. But the big thing that we need to check here is, do all these probabilities sum to 1? And we can check that by, first of all, noting that 1 over y times y plus 1 can just be written as 1 over y minus 1 over y plus 1. We need to see if that infinite series sums to 1. Well, note that that's just equal to 1 minus 1 half plus 1 half minus 1 third plus 1 third minus 1 fourth. So all of those terms are going to cancel. And we're left with 1 minus the limit as y goes to infinity of 1 over y, which of course is equal to 0. So indeed this thing does sum to 1, so it's a valid probability mass function.
Why do you need to say that f of y is 0 otherwise? You already said y can take values of 1 and 2.
Just for the sake of completeness, I mean, when you're defining any type of real valued function, you should define its value for all possible real numbers in the domain. So here we're just spelling out if y is one of these countably infinite number of values, i.e. natural number, it takes this. For any y that's not a natural number, it's 0. So now we'll discuss continuous random variables. Recall that a random variable is a function that maps a probability space to the real line, and therefore you get a new probability space that's defined in terms of the real numbers, where the set of possible events is the Borel sets, and the probability measure is defined in terms of the cumulative distribution function.
So that is still for Borel sets. It's just like the B.
Yeah.
Okay.
So we just discussed the case where y is discrete. That is, y can take on a finite or countably infinite number of values. And a random variable y is called continuous if its distribution function, that is, the probability that y is less than or equal, the big Y is less than or equal to little y, is a continuous function. The implication here is that if, I should have mentioned this earlier, but if you plot the cumulative distribution function of a discrete random variable, it will not be continuous. It'll end up being a step function that it will, for instance, so the simple example, the number of heads from a single toss of a coin, the cumulative distribution function will be equal to 0 up until 0. At 0, it'll jump to 1/2. At 1, it will jump to 1 because it will always be less than or equal to 1. It'll be a step function that will have discontinuities at 0 and 1. Random variable y is continuous if the distribution is a continuous function. That implies that it can take on countably infinite number of values, any value between 0 and 1, or any value in the entire real line. It doesn't really matter, but the implication is it can take on any one of a continuous number of values. And so, since it can take on a continuous number of values, then it doesn't make sense to talk about the probability that it's exactly equal to some number. You can show very easily the probability that it's exactly equal to any one given number is precisely 0. Rather, you have to talk about the probability that your continuous random variable is in some interval. For example, an idealized continuous random variable is, well, let's say the amount of time it takes me to finish this lecture. If you could measure the amount of time I spend talking with perfect accuracy out to millions of decimal places, the probability that I'm going to end in exactly 73 minutes and 24.2697243 seconds is 0. I mean, it's just vanishingly small, but it does make sense to talk about what's the probability that I'll finish between 60 and 70 minutes sort of thing. And little mathematical side note here, we're going to focus on absolutely continuous random variables. A function f of y is defined to be absolutely continuous if it can be written like this, that the cumulative distribution function is equal to the integral of its derivative. That's actually not the standard definition for absolutely continuous functions. There's another definition. If you read through the book chapter that I posted for the PhD students, it gives the precise definition. If you're not a PhD student that's going to take 760 one day, then I recommend that you never look at it because it will just make your head hurt. But We can talk about absolutely continuous random variables if the distribution function is absolutely continuous. The reason why we want this to be true, I'll show you here in a second, it implies that you can differentiate it, or you can at least differentiate it almost everywhere. That's actually not me being lazy with my terminology. That's a precise mathematical term that means you can differentiate it everywhere except possibly on a set of measure 0. You'll learn all about it in 760 if you take it. If you don't take 760, then you don't need to worry about this. In general, absolute continuity is a stronger condition than continuity, but a weaker condition than differentiability. As I said before, an absolutely continuous function would be a function that's differentiable almost everywhere, differentiable everywhere except for a countable number of points. If a function that's nowhere differentiable cannot be absolutely continuous, you can show. And maybe I'll give a homework problem or two about this for the PhD students so that your heads hurt less when you make it to 760, but I don't think I'm going to torture the rest of the class with this. Oh, did you have a question about this?
About the Riemann integral you mentioned.
Mm-hmm.
For now, what do you mean by?
For now probably means for the end of this class at the very least, that we even want to open this can of worms. MS students, feel free to plug your ears if you want to avoid trauma for a second. Riemann integrals. Later on, when you take 760, you may look at something called Lebesgue integrals, which is kind of a generalization of the Riemann integral. That, for instance, if you may have gotten the example of a function in calculus, where like f of x is equal to 1 if x is rational and 0 if it's irrational, sort of thing, and they always point to that as an example of a function that's not Riemann integrable. You can generalize the integral to what's known as the Lebesgue integral, where rather than doing the Riemann integral is defined to be like take partition the thing that you're trying to find the area of into a bunch of rectangles, multiply the width of the rectangle by the height of the rectangle, add them all up to get the area, take the limit of that thing, call it an integral. Great. Well, that only works if the function is pretty close to being continuous so that it makes reasonable sense to define the height of that particular rectangle. If you have a bazillion continuities like that function I just described, that won't work. So the idea behind Lebesgue integration is rather than just saying the width of the rectangle times the height of the rectangle, you can just say the measure of the rectangle in a certain sense. So for the purpose of statistics, you can say like the probability of drawing a certain set of numbers times the height of the function within that set of numbers that doesn't necessarily have to be a rectangle. So the function I just described, if you can show, for example, that the probability of drawing a rational number is 0, which it is under standard Borel measures, then you can integrate that thing by saying it's going to be equal to the value of the function when x is rational, which is 1, times the probability of drawing a rational, which is 0, plus the height of the function when x is irrational, which is 0, times the probability of drawing an irrational, which is 1. So you can define the integral in the Lebesgue world where the Riemann integral is not defined. And The only reason why I even answer that question is because if you look at the little 690 syllabus that I posted on Sakai, they want you to at least have some intuitive idea of what the heck this idea of a Lebesgue integral means. So I just explained it to you. If you're an MS student, that sure as heck is not going to be on the homework or the exam. So just, you can forget about everything I just said. And that was probably way more information than you wanted in response to that question, but just so you know, the PhD students, this is something you will probably have at least a couple homework problems to look forward to because they want you to at least have some idea about this stuff. So anyway, if the reason we want our distribution function to be absolutely continuous is because then you can define the probability density function to be essentially the derivative of the cumulative distribution function, which exists everywhere except possibly on a set of measure 0, or in probabilistic terms except possibly in a set of probability 0. Since the set has probability 0, if it's not differentiable there, we don't care. Oh, the implication of this is that if you want to find the probability that your random variable is between two numbers a and b, if you have the cumulative distribution function, of course, you can just take f of b minus f of a, but if you don't, and in practice, the vast majority of continuous distributions that we care about will be able to define the density function, but not the cumulative distribution function. You can get this probability just by integrating the density function. And in general, and I guess this is once again kind of alluding to what I said earlier, that if you want to find the probability that y is an element of some Borel set B, then you can integrate over that Borel set rather than just some interval. And again, like I said, Lebesgue integration is defined in terms of measures rather than just breaking it up into intervals where the length of the interval is the de facto measure, or I should say the width of the interval is the de facto measure of that interval. So, for example, if you wanted to say the probability that your random variable is a rational number, you could do that if you extend this to Lebesgue integration. But for this class, we won't, with the exception of possibly a couple homework problems for those enrolled in 690. And why is my slide not advancing? Okay, that is disturbing. Did my computer freeze? What's going on here? Okay, there we go. Sorry about that. Okay, so in general, a function f of x is a probability density function if and only if it's non-negative everywhere and the integral of the probability density function from minus infinity to infinity is equal to 1. So, for example, if we have a cumulative distribution function with 1 minus e to the minus lambda x for x greater than 0 and f of x equal to 0 for x less than, or f of x equal to 0 for x less than or equal to 0, is f of x a CDF, and what's the corresponding probability density function? Well, big F of x is continuous and non-decreasing, and the limit as x goes to, and there are several typos here, unfortunately. I'll try to fix this when I get home. It's supposed to be x goes to minus infinity there, is 0, and the limit as x goes to infinity is 1. So it satisfies all the properties of a cumulative distribution function. It is indeed a CDF. And to get the distribution function, or the density function, we can just differentiate the cumulative distribution function, which in this case turns out to be lambda times e to the minus lambda x. As an aside, this is the cumulative distribution function density function for an exponential random variable, which we'll be discussing in more detail later on. And second example, let's say we define a density function to be 1 over x to the r for x greater than 1, and f of x is equal to 0 otherwise. Does it satisfy the properties for a PDF? Well, it is clearly non-negative everywhere, so it satisfies the first property that we need. Does it satisfy the second property, namely that its integral over all the reals is equal to 1? In this case, we only need to take the integral from 1 to infinity because it's 0 for x less than or equal to 1. We work out that integral, and this was not worked out in the notes that they gave me, so I really hope I did this integration correctly at 1 in the morning last night. But assuming there are no errors in that integral, it should be equal to 1 over r minus 1 for r greater than 1.
So say we were asked to prove that a function is continuous and non-decreasing, how would you go about doing that?
Good question. For this particular example, I'm pretty sure there's some property somewhere that says that like exponential functions are continuous and increasing sort of thing. And for something like this, you're welcome to just use these types of properties. If you were going to do this by hand, which I don't think I would make you do in this class or in any of the other classes you would take in the PhD program. I mean, if you take 521, they might make you do something like this. But, I mean, continuity, you would probably just need to go through the properties of continuity, which, geez. What is the definition of continuity? You can tell I use this frequently in my day-to-day life. F of x1 minus f of x0 divided by x1 minus x0 less than epsilon, whatever it is. Yeah, I'm just admitting I can't remember the definition of continuity off the top of my head. If you didn't have some sort of theorem that said this type of function is continuous everywhere, you would probably just need to go through the definition and prove it. For non-decreasing, you can do certain tricks, like to say let x greater than y, and go through it until you end up with like e to the x less than e to the y sort of thing. And there are various tricks that you can do for those types of proof, and it really varies heavily depending on the function.
Is the derivative supposed to be with respect to r or with respect to x?
It's with respect to x. Good catch. There's another typo. And I mean, I guess if this whole thing gets abstract, maybe I shouldn't go too far afield here, but if they'll let you use derivatives and stuff, I mean, if the derivative's positive, that implies that it's increasing and so forth. Depending on the class, sometimes they'll let you do it and sometimes they won't. For this class, I don't intend to be really uptight about those sorts of things that you can tell that it's true just by looking at the graph, but can be kind of a pain in the butt to prove rigorously. Anyway, the moral of the story here is that f of x, the way it's defined right now, is not a PDF, but if you multiply it by r minus 1 first, then you get something that is a PDF. Oh, most of these notes I kind of discussed earlier, that for a continuous random variable, the density function f of x is not the probability that y is equal to x. In fact, if y is an absolutely continuous random variable, then the probability that y equals to x for any given x is exactly equal to 0, just because there's too many possible values. A continuum of values, the probability to get any single value has to be equal to 0. If you want to prove that formally using math language, then you can just take that's going to be equal to this limit as h goes to 0, the density function, which of course is equal to the cumulative distribution function, f of x plus h minus f of x minus h, which by the definition of continuity, which of course I have deeply ingrained in my brain, I don't know why I ever suggested that I didn't, implies that thing is going to 0 as h goes to 0, so yeah. And more generally, if B is any sort of subset of R with measure 0, then the probability that y is in that particular set of measure 0 is going to be equal to 0 as well. This is, like I said, the whole generalization of the integral, that rather than saying rather than breaking it up into a set of contiguous rectangles with a certain length, you break it up into a series of sets with contiguous measures. And so if you're integrating over a set of measure 0, that would be equivalent to integrating over an interval of length 0. It's just equal to 0. And since the probability that your continuous random variable y is equal to a specific value is exactly equal to 0, all of the below are equivalent. Probability A less than or equal to y less than or equal to b, probability A less than or equal to y less than b, or probability A less than y less than b. So we'll use the notation interchangeably sometimes because it's understood that they're all the same, because the probability that a continuous random variable equals some specific value is exactly equal to 0. And also note in passing, it is possible for a density function to exceed 1 as long as it integrates to 1 over the real line. If it exceeds 1 for just a really tiny space, such that the integral still comes out to be 1, then that's fine. You can think of a density as sort of a relative probability that y takes on a given value x. The reason we can say that is that by the mean value theorem, for a sufficiently small delta, the probability that y is in some interval between x and x plus delta, that's going to be approximately equal to the density function times the width of the interval delta. So in general, for any y, the probability, or for any a, the probability that y is in some interval really close to a is going to be approximately equal to f of a times the width of the interval. Similarly for b, so in other words, if the density function at b is greater than the density function of a, then it's more likely for y to take on values near b rather than values near a. So we can't say that f of b is the probability that the density function, that the random variable is going to be equal to b, because the probability that a continuous random variable equals any specific value is exactly equal to 0, but it's kind of a relative probability in a certain sense. And then I'll just briefly introduce this concept of stochastic ordering, and to be honest, when I went through these notes last night, this was the first time I'd heard of this in my life, and I have no idea what it's useful for. So I'm not really sure why it's being taught, but somebody apparently thought it was important enough to include in these notes, so I'll just go over it really quickly, that if you define x to be y plus 2, then x is always going to be greater than y. And if you define random variables like this, then it's possible that x is not greater than y, but most of the time it will be. So x is defined to be stochastically greater than y if the probability that x is less than or equal to some value is always less than or equal to the probability that y is less than or equal to that value. And for at least some of them, the inequality is strict. And like I said, I'm not really sure what this is useful for or why anybody will care about it, but if this shows up on the quals, then you'll at least know what the heck they're talking about. Any questions about anything today? Wow, I rambled for a bit longer than I thought I would.
I have a quick question.
Mm-hmm.
Is the empty set a countable set?
Yes. The empty set is always countable because it has to be contained in all sigma fields.